Okay, I want to do a portion of problem section 3.1, problem number 13. All right, let's assume that we have this recurrence relation already and try to find a solution from there. All right, so first thing, you have a recurrence relation. Cn plus 2 is defined in terms of Cn. So for now, I'm going to just do a little bit of rewriting. I'm going to write 9 as 3 squared, and that's just a minor adjustment. So 3 squared over n plus 2 times n plus 1 times Cn. All right. So since n2 Cn plus 2 is defined based on Cn, there's no Cn plus 1. I'm going to divide into even terms and odd terms. So let's look at the even terms first. So even terms. All right. So let's look at the C2. So C2 is going to be, right, negative 3 squared over, right, so n in this case 0, so it's a 2 times 1 and C0, right? Then how about C4? C4 is negative 3 squared over 4 times 3 times C2. Can I just write the C2 right there? C2 is right here, so I'm going to just put that in. Negative 3 squared over 2 times 1 times C0. Right? Then you can clean it up a little bit. You can see that there's a negative sign there, two of them, so it's going to be negative 1 squared. And 3 squared times 3 squared would be 3 times to the fourth power. Then you have 4 times 3 times 2 times 1. Easy way to say that is 4 factorial and C0. All right. Then you can say, okay, I'm already seeing the pattern, so you can see that it's going to be negative 1 to the first one power and 3 squared over 2 times 1 is 2 factorial C0. All right. So from here, we can see that it's going to be, so I'm going to just say so I'm looking at the pattern. So it's going to be C2n is going to be, all right, so the power is always half of the index is 2 when it's 4, and the second power. When it's 2, it's the first power. So when it's 2n, it's going to be n power. So it's going to be negative 1 to the n power. All right. Then you can see that it's a 2, 2 here, 2 here, and a 4, 4 here, 4 here. So if it's 2n, then it's going to be 3 to the 2n power. Then you have a 2n factorial. Then you have a C0 as usual. All right, so we got formula for C2n. All right, so we're gonna do formula for the odd one, so C2n plus 1. So here's the odd terms. All right, as usual, let's start with C3. So C3 is going to be negative 3 squared, just like before. And let's say n equals 1, so it's going to be 3 times 2. Right? Then you have C1. Right? Then C5 is going to be negative 3 squared over 5 in this case, so it's 3, so it's going to be 5 times 4. Then times C3, but C3 is up here, so I'm going to just put that in, so it's negative the previous one, so it's going to be 3 times 2, and then you have a C1. All right, then we can see that again. There, -1 times -1 there. And 3 squared times 3 squared would be 3 to the 4th power. And 5 times 4 times 3 times 2 is, again, 5 factorial. C1. Okay, then better yet, I'm going to make a little bit of adjustment to kind of mimic the pattern here. So we have 5 factorial. It would be nice to have 5 here. So I'm going to make that 5 by multiplying by 3 and divide by 3. So it's a -1 squared, 3 to the 5th power. So I put extra 3 there. But then 5 factorial. But to take care of that, we're going to divide C1 by 3. Right? Then I do the same thing here. So this is going to be C3 is -1 to the 1st power, and 3 to the 3rd power over 3 factorial. But you would have a C1 over 3. Right? Then we can say dot dot dot. We found C2n plus 1. Right? So let's see. So it's going to be -1 to the power, but you can see that when it's 3, 1. When it's 5, and 2. So which means that you subtract 1 from the number, divide by 2. Subtract 1 from the number, divide by 2. So it's nth power, which is nice. All right. Then you have 3 to the what power? It's 3 3rd power, 5 5th power. So if it's 2n plus 1, 2n plus 1 power. And the denominator, the same number, factorial. So 2n plus 1 factorial. Then at the end you have C1 over 3. All right, so we got that. So therefore, we can find the solution. So solution is going to look like, so therefore, our solution is going to be y equals, all right, so it's going to be C0, and the summation goes from n equals 0 to infinity. Then we're looking at the formula up here, so it's going to be -1 to the nth power. Then you pick out all the even terms, so it's 3 to the 2n power over 2n factorial x to the 2n. Then plus, right? So the constant is C1 over 3. So you have a C1 over 3. Then you have a summation just like before, and goes from 0 to infinity and -1 to the n. Then you have 3 to the 2n plus 1 power over 2n plus 1 factorial. Then you have x to the 2n plus 1, right? All right, so, but you can see that we recognize this guy right here. This is the power series for cosine of 3x. And this right here is the power series for sine of 3x. Right, so therefore we can write it as C0, some constant, times cosine of 3x, plus C1 over 3 sine of 3x. Right, so that's how you can go from the recurrence relation to the solution. All right, I hope this was clear.